Okay, thank you very much. Let's continue, and this will be the ninth session of the part 1 of this lecture about non-stationary time series analysis with modern signal processing techniques. So this is a list of references about what we will discuss in a bit. Okay, as you can see from the I just list part of it. There's actually several many. We will talk about frequency, capture, and cross capture, and so on. Okay, and there will be something called D-shape, or it's called wave shape function analysis, whatever it is. The algorithm is called D-shape. I don't know. I don't think I will have time to discuss from a Nunjiang. There's a number theory approach to do signal processing, but I hope I will have time. But let's see. So this is the QR code. If you have interest in playing with the algorithm, everything's included, which you should be able to download and reproduce and apply to your data set. So the motivating example of this kind of work is fetal ECG, fetal electrocardiogram. So when female is pregnant, one main concern we all have is the baby's health. But how to see the baby's health? That is the question. As I showed you, I already showed you this picture in the first session. What you can do is you can put ECG leads on the female's abdomen and record it the transabdominal maternal ECG. And this transabdominal maternal ECG contains two ECG components. One is maternal heartbeat. The other one will be fetal heartbeats. And those small spikes are fetus because we have simultaneously recorded fetal ECG for a confirmation. So those small spikes are not artifacts, but fetal ECG information. The question is now reduced to the following. I give you a summation of two ECG signals. Would it be possible to decompose the signal into maternal's ECG and the fetal ECG so that we can get fetal electrophysiological information or even obtain fetal heart rate variability for heart rate variability analysis? Again, this is the single channel blind source separation. Single channel blind source separation. Just like you have one channel only, but you need to identify who is talking from that channel, which is a super challenging signal processing problem. But from our ear, it's maybe surprisingly easy. Right? From a party, if you want to listen to Hun, you can just focus on how he talks, and you can find him. The challenge, as I already mentioned before, there's only one channel or a few channels. The signal is very spiky, so it's a broad spectrum. Noisy, artifacts may be non-stationary. Frequency, amplitude, oscillatory patterns are all changing from time to time. Then what can you do? What can you do? The algorithm will be called D-shape algorithm. And I will show you first example of what's going on. I give you three oscillatory components, as you can see. Those signals, those three components, are all oscillatory, as you may agree with me. But their oscillatory frequencies are different. This one obviously is faster. This one obviously is slower. And now I sum them all together. This is a signal I give you. So as a signal processing guy or data analyst, I may ask you, hey, I give you this signal. Could you please do some analysis and tell me some information about what's inside? What can you do about it? That will be a question. As we have learned so far, we may say, hey, okay, now we know it's very non-stationary, very good. So how about if we just apply short-time Fourier transform, get spectrogram, or using synchronous squeezing transform? Maybe we can get something already. Yes, you can. And this is the result. without adding any noise, this is the short-time Fourier transform. You can see there are many components. Well, sometimes it's weak. Well, what is inside, it is maybe not that easy to say immediately. Now you may say, oh, it's because short-time Fourier transform, the contrast is low, so let's try synchronous squeezing. But in synchronous squeezing transform, you say, hey, you can see all the components, contrast is higher, but still it's hard to say what is what. The only thing you can say is, oh, there are multiple components, many components. Yes, many components. That's maybe the only thing you can say. But what else? What else? And this is the real example. As I told you, the transabdominal maternal ECG. There are some big spikes, or wider spikes. Though they are for maternal ECG, and there's some shorter, narrower spikes. They are for fetal ECG. And this is the short-time Fourier transform spectrogram. Again, which one is which? What are you reading right now? It is not very easy. It's not very easy. Okay. So now you may have a basic understanding. Using short-time Fourier transform or synchronous squeezing may not solve our problem. So we want to introduce a new algorithm that can help you to solve this kind of problem. The algorithm is called D-shape, and I will use this signal to illustrate how you get how the D-shape algorithm works. In this signal, you can see that it oscillates roughly, or not roughly, it oscillates 2 times per second. That is, the frequency is 2 Hertz. Frequency is 2 Hertz. But the oscillation is not sinusoidal, it's spiky. Right? The magnitude from large 1.5 reduced to 1, roughly. That is the signal, keep it in mind, 2 Hertz, very simple, just 2 Hertz, and the spiky oscillatory. Now, we have learned short-time Fourier transform, so I don't need to repeat it. You take a window, truncate it, and evaluate short-time Fourier transform, so you get spectrogram. What you get is 2 Hertz, 4 Hertz, 6 Hertz, right? Very simple. Why? Because the frequency oscillates at 2 Hertz, and you see many multiples. That's what I give you. So you have fundamental frequency and all its multiples. Easy. Now, what's next? The next thing we can observe is something very trivial. If you now focus at one fixed time, like let's say 20 seconds, and you look at the frequency axis, do you see anything specific? You will see that in the frequency axis, the spectrum is oscillatory again, right? Every 2 Hertz, it oscillates once. Every 2 Hertz, it oscillates once. Which means, in the frequency axis, it becomes another oscillatory signal. So we may consider to use this oscillatory pattern and do something. And this something is called capstone. And what we do is, we take short-time Fourier transform, we take natural log, absolute value, and take natural log, and evaluate inverse Fourier transform. I will explain why we need to do it, but this is the consequence. Because the oscillation here in the frequency domain is every 2 Hertz. So in the frequency domain, after inverse Fourier transform, we come back to the dual space. That is the time domain again, which is half second. So you see 0.5, 1, 1.52, this becomes less clear. So you can see what you get in the capstone in the frequency domain. It is the period, and it's 2 times period, 3 times period, and so on. Where the period is 1 over frequency. Good. No? Now, we need to explain what's going on. What do I see here? Captron, and this is what? Frequency. What is it? Turns out, this is the terminology introduced back in 1963. The captron is nothing but you reverse the spect. Back, you get captron. Not spectrum, but captron. Frequency is you reverse the consonant. Frequency, and you get frequency. That to emphasize that we are working with the dual space. Okay? And this is terminology. Why do we care about natural log? The idea is very simple. So if you remember, the oscillation is one periodic. Because it's one periodic, so what you have S of t can be written as summation alpha L cosine 2 pi L t plus beta L. L is from 1 to infinite. And right now, you have the oscillation in the frequency domain, which the strength is indicated by alpha L. So you have different strengths at different frequency. And this different strengths at different frequency somehow can be viewed as a uniform spike multiplied by a low frequency component. And because of multiplication, if you take log, multiplication becomes summation. This uniform spike keeps as a uniform spike, but the low frequency component after taking natural log is still low frequency component. So that we can get a very enhanced oscillatory pattern after taking natural log, and take the wave shape function dependent strengths of the Fourier series, well, strengths, harmonic strengths, decompose it into a low frequency component. So that you do Fourier transform, the high frequency oscillatory information will be enhanced, and the wave shape related information will be hidden in the low frequency information or low frequency information in a low frequency area. So that is how you get this short time captron, because we fix at each time and evaluate its frequency. Now, the key step of the D shape is using the following fundamental relationship in between period and the frequency. That is, period is the inverse of frequency, and frequency is the inverse of the period. So what we do is, we just take the captron and we reverse the y-axis. We reverse the frequency axis by 1 over c, and you reverse from the frequency time domain information to the frequency in the frequency domain. And once you apply this 1 over c, reverse the frequency axis, you get 1 over q, which is its fundamental component, fundamental frequency, and 1 over 2q is half fundamental frequency, and the 3q will be 1/3 fundamental frequency. And now, if you compare these two pictures, what are the common information? The fundamental frequency, isn't it? The fundamental frequency is the common information. And there will be multiples, and there will be divisions. So that if we want to recover the fundamental frequency, what we can do is nothing but, hey, let's do multiplication. Let's do multiplication. Okay? So that the division is cancelled by this part, and the multiples are cancelled by this part. So that there will be fundamental frequency remains in the very end. So that is the D-shaped algorithm, which you can view it as a nonlinear filtering technique for the short-time Fourier transform. It's a nonlinear filtering technique. And there is a small numerical issue that is called soft log. So technically, if you really take nature log, log is a very unstable operator. In particular, when the value is very, very small, it may blow up. So we consider to use material expansion to approximate nature log, using the fact that the x raised to gamma 1 minus 1 divided by gamma. If you take gamma to be 0, it will approximate nature log, something like that. So this soft log is more robust because it is just polynomial, and we found that it works very well in practice when you take gamma to be 0.1 or 0.3. So that is overall the basic idea of numerical implementation. All the others are similar. There are surely some technical challenges. For example, how to take 1 over c, but then those numerical implementations can be transparent. You need just, well, but I will not discuss details here. You can check the code and method implementation. So here is an illustration of everything. For example, this is a PPG signal, and this is, you take a window centered at 25th second, and this is the window signal, and you evaluate its the Fourier transform or power spectrum. That's what you get: 0 hertz, right? 1.2, 2.4, 3.6, etc. And now, if you take nature log, or you take just 0.1 power, you see it is spike, spike, spike. Those very unevenly high spikes, they are more even after taking 0.1 power. Okay, and so that once you reverse the y-axis, you get something you are interested. You do Fourier transform, you have something you have interest. That is the frequency. And then this is after you take reverse. This coming back to frequency, then you get 1.2 hertz, 1.2 hertz, and there is not too much remain. But there will be all the high frequency information was squeezed into the low frequency part, so that you have only one common component, the fundamental frequency. So if you multiply these two guys, then you get what you want. So this is a visualization of everything. So let's come back to this simulated signal. Again, there are 3 components, and this is a summation. And this is the short-time Fourier transform, which I have shown you. And this is the inverse, this is short-time capture transform. You can see that is you have the components, you have interest, a period, and its multiples, but it's not very clear to see what's going on here. Yeah, and this is the inverse one. After you take inverse, you have the component, and its divisions. There are many things in the bottom. So if you multiply short-time Fourier transform and the inverse short-time capsule transform, that is what you get. 3 components. And there is an interesting part here where instantaneous frequency crossover. And this kind of crossing over instantaneous frequency is something we need to discuss separately, because when 2 components have crossing instantaneous frequencies, then traditional time frequency analysis is incapable of handling it. And we need new ideas. And the new idea is called triplet. And we will talk about this triplet transform, if time permits, in the end of this part. But here, I just want to show you this kind of multi-mixing or crossover instantaneous frequency issue, which is a very serious one. And this is I should have and this is after you get the D-shape short-time Fourier transform, you can apply synchronous squeeze. You can apply the reassignment rule to the short-time Fourier transform, and you get 3 very clear enhanced lines in the time frequency domain. And on the right-hand side, I just superimpose the ground truth for you. because the signal is generated by me, so I know the instantaneous frequencies. And if you see the superimposing, that gives us almost all information we need for instantaneous frequency. What we need more later is how to use this information to obtain the decomposition, and we'll come back to this issue hopefully on Thursday. And moreover, the signal is usually noisy but not clean. And when the signal is noisy, what happens? So this is a clean signal, and this is the noise I generated, which is, I remember, RMA11 noise, and the innovation process is student T4. So you can see there are some spikes, big noises. And this is a summation, sum signal. I give you this noisy signal, and I ask you to do the analysis. What can you get? This is the short-time Fourier transform spectrogram. You can see like before, but now it's more complicated. And now, this is the D-shaped short-time Fourier transform, which looks quite good, isn't it? Oh, and I haven't shown you D-shaped short-time Fourier transform, but oh yeah, I only show you D-shaped synchronously. But anyways, you can see this. And if you compare with the ground truth, it recovers the ground truth very well. Okay, so now it seems to work well. Before I show you the practical applications to real-world data sets, let me quickly show you some existing theoretical works, theoretical results, and some open problems. So the first theoretical support can be quickly shown using the following simple calculation. Again, let's consider a function f which has fixed amplitude and fixed frequency. And s is a one periodic function. So if you just take this function and use Fourier transform, that is what you get. Ck, okay, C0t, alpha k, and this is the magnitude of each harmonics. Now, suppose S is good. Well, but it's non-sinusoidal. Okay, that is N is finite. Very nice. We don't even need to worry about convergence issue and so on. Now, what you can do is you evaluate its short-time Fourier transform. And you evaluate its short-time Fourier transform. This is immediately what you get with the window H. And not now, because it is a cosine function, you just need to rewrite it as exponential I plus exponential minus I, right? And you evaluate Fourier transform, and it's just a Fourier transform of the window function, right? And this is what you get. But now it's from minus n to n. Very good. And as I mentioned, what we want is to take natural log or take gamma power. Let's assume we want to take gamma power. To simplify the discussion, we assume that h hat in the frequency domain has a very narrow support, so that there is no overlapping of different h hat for different k. And this is an easy assumption we can make. So there is no overlaps. But if there is an overlap, we can easily handle it, but that will just be an error term. Because there is no overlap, so taking the gamma power is equivalent to exchange summation and the absolute value gamma power into it. Once you get this point, you can easily rewrite everything as the convolution using the delta major formula. So you just put the h hat, gamma power, absolute value gamma power at each frequency. And that is what you have here. Now, what we want is, after taking natural log or gamma power, we evaluate inverse Fourier transform or Fourier transform. Then this is the capture. Okay, and by applying Fourier transform to the convolution using Plancherel rule, that is what we get. So you have something Fourier transform or Fourier transform gamma power, which you have to be careful because usually this guy may not have Fourier transform, so everything starting from this point has to be written in the distribution sense if you want to make it very rigorous. And this will be the CK gamma, and you evaluate Fourier transform. And this guy, if you put all the summation together, it will be a periodic function, but with frequency 1 over C0. But remember, this is now in the frequency domain, so this is period. So now, you see, this guy is a periodic distribution with the period of length 1 over C0. So from this point, we can get instantaneous period and its multiples. And we can then continue with the inverse Fourier transform. And to inverse the frequency axis to get frequency axis. And then you just need to be careful about how to apply inverse to a distribution in general. And there'll be Homender's lemma that helps you to develop it. So you can get the theoretical support, but everything will be in the distribution sense. And when you have multiple components, then we need to further control the overlapping before taking the gamma power by taking the Erdős-Thünen's inequality, which we will elaborate in a bit. And if you have an adaptive non-harmonic model, that is the amplitude and the frequencies are not fixed, then we can just use the slowly varying property to locally control the errors so that we can say what's going on in the end.